Okay, we left at the end of last lesson with this bit of a conundrum, in a sense, where we got this idea that light somehow is it's a particle, or behaving like a particle, and these photons. So, as I mentioned then, it was Einstein who was left up to explain the photoelectric effect, and so he got a Nobel Prize in 1921 for this. All right, and what he said was that the energy was not spread out evenly across a uniform wavefront, but in separate lumps or packets of energies. All right, and that these packets depended on the frequency of the light, and that more intense light contains more packets, but each packet has the same amount of energy. So that explained the immediate ejection, because all you need is just a photon with enough energy, and bang, there it gets absorbed, boom, and off you go. So you only need one. And then the frequency, if that's too low, each photon not enough energy, no matter how bright the light was. So if we have a look at another graph very similar to one I did before on the photoelectric. So here we've got three different cathode materials: sodium, magnesium, and copper. And we've got these points on each of those that we use to plot. And so that's the kinetic energy of those electrons at certain frequencies of light. Now, and we see that there's these distinct places, which we call the threshold frequency, all right, that below which a particular material can't emit electrons. So for copper, it's way up here, 11 by 10 to the 14 hertz, and so on. For the other two, all right, so and if we extrapolate back like we did last time, the copper one comes back here at about 8, and so that's the work function. So that's how much energy it takes for an electron to make its way to the surface of copper before it gets ejected. All right, so different cathode materials, different thing, and as it says here that the slope is Planck's constant, all right. So if we have a look at some equations, or equation of the line, okay, and this is out of your notes. So the equation of the line, the kinetic energy max, HF minus W. So by explanation there, HF is the energy delivered for the photon. The electron loses energy when it makes its way to the surface, and that's W, the work function. And so the energy we've got left, HF minus the work function, is the kinetic energy of the photoelectron, the electron that shoots out. So there's a couple of little notes about this first of all, before we get on to some examples. So W is the minimum amount of work done getting to the surface, called the work function, talked about that. And the work function is characteristic of the cathode material, so different material, different work function. And it's HF0. Now F0, just to remind you, back here, so F0 is here, wherever the line crosses the frequency axis. That's the F0. That's and also don't forget that sometimes we measure in electron volts, just because it's a little bit easier in talking about numbers, because we don't have to worry about these massive powers of 10. And don't forget that's your conversion. Alright, so an example. Yellow, green, right, wavelength, that's an important bit. stopping voltage 0.8, and the mass of the electron, there it is, and that should be 10 to the minus 31. Didn't come out very well. That is, find the work function of the metal in both joules and electron volts. Alright, so we know that our maximum kinetic energy equals HF minus W, the work function. Alright, so what we're after is the work function, so we're trying to find that one there. So our maximum kinetic energy, well, our kinetic energy is going to be related to our stopping voltage, because E equals QV. So that will be 1.6 by 10 to the minus 19 on times 0.8, which is, now I'm doing this a little bit different than the way it's set out in the notes, but still the same thing. Alright, so 1.6 by 10 to the minus 19 times 0.8, and that's 1.28 by 10 to the minus 19. Now, that's energy that we're talking about here. That's the kinetic energy. Alright, so that's the energy that's got to be to stop that electron, electrical energy to stop the electron. So that's the kinetic energy, 1.28 by 10 to the minus 19. H, Planck's constant. Okay, so I'm going to work it in joule first, 6.63 by 10 to the minus 34 times the frequency. Well, that's not going to work for us any good because we haven't got the frequency. So but what we've got is the wavelength, haven't we? So let's get rid of that and come back to it later, because we need to, using V equals lambda F, then we know that the speed of light is 3 by 10 to the 8, the wavelength's 500 by 10 to the minus 9 nano, times the frequency. So the frequency of that light, 3 by 10 to the 8 divided by 500 by 10 to the minus 9, that comes out to 6.0 by 10 to the 14. Alright, so let's go on to the next page here. Remember, the kinetic energy max equals HF minus W. Kinetic energy max, there it is, 1.28 by 10 to the minus 19. HF, we've worked that as well, there it is, 6 by 10 to the 14, and H, of course, 6.63 by 10 to the minus 34, times F, 6 by 10 to the 14, minus the work function. Let's need to work out what HF is. So 6.63 10 to the minus 34 times 6 10 to the 14 is 3.978 by 10 to the minus 19 minus the work function. Alright, so if I add the work function to both sides and subtract this, I get that the work function is 3.978 by 10 to the minus 19 minus 1.28 by 10 to the minus 19, which is 2.698 by 10 to the minus 19 joule. And then we need to change that to electron volts by dividing by 1.6 by 10 to the minus 19. And when you do that, you get 1.686 electron volts. All right. So there's that first example. All right, there's another example. Let's have a look at the second example. It's got a few parts to it. Okay, so kinetic energy, ultraviolet light, a wavelength 200 nanometers, incident silver surface, work function of silver is 4.7. What is the kinetic energy of the fastest moving electrons? All right, so we've got energy of a photon. Now remember there's HF for that, but also there's HC on lambda, and that's the one we're going to have to use. Now because they're asked, our work function here is in electron volts, I'm going to use the electron volts version of Planck's constant, times it by the speed of light, divided by 200 nanometers, 10 to the minus 9. And we do all of that. Again, I'm doing this slightly differently than I did in the notes, but you get the same answer, 4.1, 10 to the minus 15, times 3 by 10 to the 8, and divide all that by 200 by 10 to the minus 9, and you get 6.15 electron volts, because I used the electron volt version of Planck's constant. All right. All right, so I've just noticed that there's an error in the notes there. So with the final answer. All right, so your kinetic energy max is HF minus the work function. Now HF we worked out, we used the energy of the photon, and that's 6.15 electron volts. And then we are going to take away the work function, which we're told is 4.7 electron volts. So when we take that away, we get 1.45 electron volts, not 56.8 as it says in your notes. So clearly I've pressed some wrong buttons there in some way. All right, so there's part A. Now part B, all right, part B, that's kind of messing with your head there. Kinetic energy of the slowest moving electrons. Well, the slowest electrons would be stopped. All right, so the slowest is stopped. So if the slowest is stopped, then their kinetic energy would of course be 0 electron volts. All right, so cutoff frequency for silver. So remembering what we said, that the work function and the cutoff frequency were related. All right, so the cutoff frequency is the frequency where the energy is just enough to get the electrons to the surface, and the work function is the amount of energy it takes to get to the surface. So they're the same thing. So if we know the work function is 4.7 electron volts, so I'm going to use the electron volt version of Planck's constant. And then, so then we divide 4.7 by Planck's constant, And the answer comes out to be 1.15 by 10 to the 15 hertz. Oops, it doesn't look like an H, does it? Hertz. Alright, there's another couple of bits for these. So the cutoff wavelength for silver. Alright, so we just figured out the frequency and the cutoff wavelength. Let's put up those parts first before I get to... Alright, part D, the cutoff wavelength. Of course, the wavelength is related to the frequency by the speed, and of course we know the speed of light is 3 by 10 to the 8 times the frequency, which was 1.15 by 10 to the 15. So divide both sides by 1.15 by 10 to the 15, and you get that the wavelength is 2.61 by 10 to the minus 7 metres. Alright, now that's a massive thing, but if I move that decimal point a couple of places so that it's 261, then that's then nanometers. Alright, the cutoff potential for silver, so E equals QV. Alright, and VO. So we know what the charge on an electron is. The energy involved with the work function, well, we know that with the work function's 4.7 electron volts, which is great, but for this equation we've got to have the energy in joule. Alright, so we need to change that. 4.7 by 1.6 by 10 to the minus 19. Alright, which is 7.52 by 10 to the minus 19 joule. And so when we make that energy, 7.52 by 10 to the minus 19 equal to the charge on an electron, 1.6 by 10 to the minus 19 times V naught. And then divide both sides by 1.6 by 10 to the minus 19, you get 4.7 back. 4.7 volts. Which when you look at that, 4.7, it's the same as the work function, but it's not a coincidence that it's the same as the work function, alright? Because electron volts is the energy given to one electron when it's accelerated through a voltage. So 1.96, by 10 to the minus 19 is one electron. So one electron gets 4.7 electron volts. You need a voltage of 4.7. So no coincidence that they're the same. Alright, so there's our equation and all the rest of photoelectric. So then what some bright spark came up with and said, well, if light is these photons, which are these particles, then particles should have momentum. Alright, and so here's this. So the velocity of a photon is the speed of light, and we know that momentum is mv. So the momentum of a photon then should be mc. Now, Einstein had an equation E equals m squared, EC squared, and we know that the energy of a photon is E equals hf. So if we equate those two things together and say that mc squared should be equal to hf, and divide both sides by c squared, then the mass of a photon should be hf on c squared. And then if we whack that up in here, with here, let's get rid of that, let's use another colour here. So if we take this, let's use another colour. If we take this and put it in here, then what we end up with is that the momentum of a photon should be hf over c squared times c, which of course is hf over c. All right. Now, if we rearrange a few other things, because c is lambda f, and so we put lambda f on the bottom, then the f's cancel, and it's h over lambda, and of course it's also would be the energy over c as well. All right. So, by looking at that, and you're looking at this, you can say, oh well, a photon does have some sort of momentum that we can theoretically calculate. So let's have a look at an example. All right, so here's our, what's the momentum of photon of red light with wavelength 650 nanometers. So if we use the version, this one here, P equals H on lambda. Now with these ones we always need to use the joule version. Right, so that's 6.63 by 10 to the minus 34 over the wavelength 650 by 10 to the minus 9. And then when you do that on your calculator, you get 1 point, it should be 4 there, 1.02 by 10 to the minus 27. And seeing as that's momentum, it's kilogram meters per second. So as you can see there, 10 to the minus 27, it's not much momentum at all. However, there is some momentum. So theoretically, we can calculate that there's some momentum. All right, so waves got their energy in packets called photons. These photons, we can calculate that, theoretically they've got this momentum. So then, what about the other way? What about matter then? Because does matter have waves? And it was a French bloke, French prince, who come up with that idea. All right, so Louis de Broglie postulated all moving particles have waves associated with them. All right, so this is 1923 after all of this stuff's going on. So he's come up with the idea then that particles can have wave properties. So you should be able to work out a wavelength called, and we call them de Broglie waves. And so with some predictions we can work out some wavelengths. So seeing as we know that the momentum is h on lambda, that's the momentum of a photon, the momentum of a particle is mv. So if we put those things together, now if we put h lambda equals mv and do some rearranging, we can find that the wavelength will be h over mv, which of course is h over the momentum. Alright, so he said, alright then, we should be able to, if we're putting those things together, work out a wavelength. So theoretically, let's have a look and let's work out some. Alright, so we can work out the wavelength of any particle. And so here's an example here, 1 kilo mass travelling at 30 metres per second. So if we use lambda equals h over mv, h, need to use the Joule version, mass is 1, velocity is 30 metres per second, and when you do that calculation, you get 2.2 by 10 to the minus 35 metres, which obviously is an extremely small wavelength, and probably something at this point in time with the technology and everything that we have is something that perhaps cannot be detected. But in terms of our particles that we have, 1 kilo is really heavy, and 30 metres per second is actually not that fast. So if we go down to something small like an electron, which may be moving very fast, and we can get them moving very fast, let's have a look at what the wavelength would be then. Alright, so here's our electron, h over mv. Now the mass of an electron, so 6.63 by 10 to the minus 34 for the Electron Volts version there. Mass of an electron is 9.11 by 10 to the minus 31. That's something you would look up or be given. Times how fast it's going, which is 2 by 10 to the 6. Now when you work that out, you find that that's 3.6 by 10 to the minus 10 metres. Which you might think, oh, well, that's pretty small too, 10 to the minus 10. But it just so happens the spacing between atoms in crystal structure is about that. So, therefore, we should be able to observe something. So, that leaves us to electrons as waves then, if that's what we can. Prediction says. Alright, so electrons as waves, so if that was correct, then we should be able to have some wave behaviour exhibited. Now, diffraction depends on the slit size and the wavelength, and if they're about the same, we get diffraction, and as I've already mentioned, atoms in a crystal structure about the right. So then there was a few different, over the years, a few different people. So 1927, Davison and Germer. Oops, name spelt wrong there. And G.P. Thomson, J.J. Thomson's son, they performed experiments showing diffraction. And Davison and Germer also looked at the wavelength, and they found that that was correct. And so 1937, these people got a Nobel Prize. So what does it look like? Well, it looks like this, and this is in your notes. Alright, so here's some diffraction. So it's the same crystal. So this one here on the left is X-rays, and this one here on the right is electrons. Right, fired at, both of those fired at the same crystal. Now you can see with the X-rays, because they've got a much smaller wavelength, so that ratio, wavelength over W, alright, is quite small, less than 1, and so we get significant diffraction, whereas the electron wavelength not quite as small. So the pattern's the same. So you look at these outer rings here. All right, so there's something there. There's a double ring here, a double ring there. Okay, so it shows that there is a diffraction pattern with electrons, albeit not quite as clear as with X-rays. So with some of these things, the issue is not whether or not the theory is correct, but whether or not we can actually design an experiment. It's a test. Alright, so eventually, only relatively recently, electrons have been able to show diffraction patterns, and then there's some other patterns with heavier ones that are now being shown. Alright. Okay, so that image that I just put, that's the one referred to here, 7.4. Scattering X-rays and electrons off a sample of tiny crystals. The X-rays used, there's the frequency and speed of light. So first of all, part A, why is a circular diffraction rather than a row of fringes as we've seen earlier? Well, the simple answer to that is that the gap is not a vertical slit. Okay, so it's a gap between atoms in a crystal structure, and the atoms in a crystal structure are not just a vertical slit. Okay, so there's kind of like a box here, if you like. Alright, so they're zooming through there, and so it's a two-dimensional thing that it's going to, not a vertical slit. So that's the answer to that one. So since the two diffraction patterns show exactly the same fringe spacing, what conclusions could be made about the electrons and the X-rays? Alright, so if they're exactly the same fringe spacing, and it's exactly the same crystal, the simple answer is, for B, is that the gap size and the wavelength are the same for the X-rays and the electrons. Alright, and then C. Let's go to C. C says determine the de Broglie wavelength. So the wavelength, one of the versions, let's go back here, and again, and again, and again. Oh, going off back a few pages. Oh, here we go. Alright. So we're looking for the wavelength of the electrons, and that equals to the wavelength of the the X-ray photons, I should say. And right, sorry, we didn't need to go back there, so I've saved you, but getting dizzy. So V equals lambda F, of course, and V is C, and lambda F. So lambda, of course, is just C over F. That's what I was looking for. Didn't need to search all that way there. So what we know is the wavelength of the electrons. So we're asked the wavelength of the electrons, but what we said in part B was that the wavelength of the electrons and the X-rays is the same. So C is 3 by 10 to the 8, and the wave frequency of the X-rays is here, and so the X-ray wavelength and the electron wavelengths will be the same. So if I work out the X-ray wavelength, I'll get the electron one. All right, so it's 3.6 by 10 to the 8.6, sorry, 8.6 by 10 to the 18. And when we do this, 3.5 by 10 to the minus 11 metres. Alright then, part D. Compare the momentum of one electron to the momentum of one X-ray. So the electron, the momentum is h lambda. And so if the wavelength is the same, then what that means is the momentum must be the same. So equivalent momentum. Alright, so finally, brings us to the question. What is light? So that's the question. What is light? And the simple answer, it depends. Depends on what? Depends on how you're looking at it. Alright, what it's doing. Alright, so we've got models. So we've got the wave model. Now we've got also the particle model. And so there's, how do we put all of that together? Well, there's a complicated thing called quantum mechanics, which provides a mathematical model that puts these things together. So Schrödinger and Heisenberg, two very famous physicists, have put that together to draw that stuff together. But for us, as I said here, it depends how you're looking at it and what it's doing. So what do we need to remember? We need to remember that the models don't provide a physical picture, all right, but they give us something that we can kind of visualise, like waves, particles, and puts the behaviour. So what we do is we accept this idea of wave-particle duality. So not that light is a wave and a particle at the same time, but depending on what you're doing with it, it behaves like a wave or a particle. So when we take particle for light, we're talking about photons, so photon particle model. So here's some behaviours of light. So things like refraction, diffraction, interference, reflection, even intensity, we can do by the wave model. And the wave model does well for them. The particle or the photon model, well, that does reflection, intensity, photoelectric and quantized energy levels. Now you notice though that there's those two down the bottom that can only be exposed plain by the particle model, and there's these ones up the top here that can only be explained by the wave model. So reflection and intensity, we can use either model, but for those other things we've got to use a specific model. Alright, so that's it for this lesson. So again, there's quite a few videos on the website there for you to have a look that explain, and they've got, you know, animations and things that look a bit better than what I can do here. There's also one photoelectric effect showing light shining on something and electrons jumping off. Also, don't forget, if you have any issues and you need to check with me, make sure you do that.